Hi all, I'm Zeng Yuko and I'll be presenting our work on SideInfNet, a deep neural network for semi-automatic semantic segmentation with side information. This is joint work with Dak Tan Nguyen, Kwang Trang Chong, Sai-Kit Yong, and Alexander Binder. Consider the task of semi-automatic semantic segmentation, which learns to map image pixels to class labels with the aid of side information. Side information can come from different modalities or even represent human annotations in the form of expert brush strokes. Human annotations are especially essential when the task at hand has a high cost of failure, such as in the medical domain for medical segmentation. In these cases, quick, rough annotations from human experts can be highly useful in guiding the model output. SideInfNet is a proposed network for tackling the semi-automatic semantic segmentation task. It is an end-to-end trainable model that spatially combines side information with input images. SideInfNet contains several novelties in its architecture, which are described in the following slides. For the ease of description, we'll describe it with respect to zone segmentation, where we wish to segment an overhead satellite image into different urban classes, such as commercial, residential, and industrial, with the aid of geotagged street-level imagery. However, the network design is very general and applicable to a wide variety of datasets, as we'll showcase later on. The first key component of SideInfNet is its segmentation backbone network, which performs the baseline segmentation over input images. For zone segmentation, the main input to this part of the model is the overhead satellite image. In our experiments, we use DeepLabResNet due to its speed and segmentation quality, but also experimented with other segmentation networks and show that our proposed SideInfNet has significant improvement over prior work, even when the same segmentation backbone network is fixed. We note that this part of the model is very general and can be replaced with any other state-of-the-art or domain-specific segmentation network with minor tweaks. The second key component of SideInfNet is the Spatial Information Processing and Distribution Network. For this part of the network, the side information is processed separately from the main images due to significant differences in modality, locality, and other features. First, domain-specific pre-processing is performed on the side information, and this may either be a learned network or a pre-trained network. For example, in zone segmentation, we use a pre-trained Places 365 convolutional neural network to extract feature vectors, which are then passed into a fully connected layer and spatially aligned according to their geocodes. This is resized to be the same dimensions as the input overhead satellite image, which may vary as DeepLabResNet scales images for multi-scale inputs. The result is a sparse and spatially aligned feature map, and we noted in early stages of experimentation that this sparsity resulted in very poor performance. In order to address the sparsity in the feature map, we performed several levels of spatial distribution before fusing the feature map with the main segmentation network. We perform a series of fractionally strided convolutions with 3x3 filters of 1s. This has the effect of distributing spatial information directly to the neighboring 3x3 region. We weight this operation with a learnable scalar, wi, and take the mean across overlapping filters. By repeating this operation n times, each feature vector can be spatially distributed to the neighboring n by n regions. And an advantage of this method is that it is not only intuitive, but it is highly computational and memory efficient, requiring only a single pass during inference time. Lastly, to further improve segmentation performance and quality, we add conditional adaptive inference gates to the segmentation backbone. At each residual layer, a gate is conditional on input to the layer that outputs a binary decision, whether to execute the layer or skip it. Intuitively, this allows the network to learn to skip execution of unnecessary layers, improving performance of the network as well as segmentation quality of the final result. To display the efficacy and generalizability of SideInfNet, we experiment on 3 diverse datasets over a variety of image inputs and side information, which will be described in the following slides. The first dataset is zone segmentation, which we have been describing previously. In zone segmentation, we are provided with low-resolution overhead satellite images, as well as geotagged street-level imagery taken on the ground. We wish to produce segmentation outputs of urban zone classes using these 2 inputs. The second is breast cancer histology segmentation, where we have high-resolution whole-slide cell images, as well as expert annotated brushstrokes describing possible classes and suspicious regions at each spatial location. Lastly, we also run a case study on urban segmentation, where we wish to segment over very high-resolution overhead images and expert brush annotations. SideInfNet significantly outperforms previous work on the 3 datasets. In particular, SideInfNet has much higher gains over previous work when brushstroke annotations are used, suggesting its generalizability in being able to incorporate both image information as well as brushstroke information, 2 very different modalities. In addition, SideInfNet is also significantly faster than previous semi-automatic semantic segmentation models, especially for high-resolution images. For more details on speed, we refer viewers to our paper's supplementary material. Here, we present several qualitative results on the 3 datasets. This first slide showcases the qualitative outputs of several semi-automatic semantic segmentation models on 3 US cities for zone segmentation. In general, we observe that SideInfNet generally produces much more refined and crisp outputs that better match the ground truth. In addition, SideInfNet also appears to be able to better utilize local photo information to produce more specific outputs, such as this region in red for the San Francisco city. Similarly, on the Beck and Zurich datasets, SideInfNet is able to better incorporate brushstroke annotations to produce more accurate and reasonable outputs. This suggests its generalizability and ability to adapt to a variety of site information modalities, as it's able to outperform previous work on both photo data as well as brushstroke annotations, which present very different types of site information. To better understand the various contributions of the SideInfNet components, we run an ablation study on the zone segmentation dataset. We observe that simply concatenating the site information as input to the deep lab ResNet model is insufficient. This produces almost no improvements in accuracy over the baseline model that does not use site information at all. With the inclusion of our proposed spatial distribution network, we achieve very significant gains of 14%, promoting the efficacy of our distribution method in this task, where site information is generally sparse. In addition, we also observe slight improvement in performance when we include our conditional adaptive gates into the model. SideInfNet achieves its best performance with an execution rate of 60%, meaning that the gates allow an average of 60% of layers to be executed on a single forward pass. In addition, this also slightly improves computational efficiency during inference time. To conclude, in this work we examine semi-automatic semantic segmentation, which is a compromise between fully automatic and manual segmentation. These types of models are essential in various domains with high costs of failure, where fully automatic models may not be readily accepted yet. A prime example of this is in the medical field, where human experts are still required to validate the automatic output of models. We propose SideInfNet, a general network applicable to a wide set of semi-automatic semantic segmentation tasks. On a diverse set of datasets, we showed that SideInfNet outperforms prior work in incorporating both image and brushstroke site information, which points to its efficacy as a general end-to-end trainable network for fusing various types of site information with image input. Thank you for listening to this presentation, and for more details, please check out our full paper.